Good mid-morning. Who's here for extra credit? Cool. Welcome to Livermore and the Bankhead Theater, and thank you for coming to the first of 4 Science on Saturday presentations. The Lawrence Livermore National Laboratory produces these science presentations with the help of local educators. So I want to say a big thank you for the Livermore Lab. Our topic today is proton therapy for cancer, addressing a big problem with a small machine. Now, when I was growing up, and yes, it was quite a while ago, the movies always had some kind of sci-fi gun, a blaster or a ray gun of some sort, and the bad guy shot 40 times, the good guy shot once and made their mark. Well, that's Hollywood, and today's lecture is about a very special ray gun, and the villain is called cancer. To talk about that special ray gun are George Caporaso, the Livermore Lab scientist, and Tom Schiffler, a teacher at Granada High School. Dr. Caporaso obtained his bachelor's and doctoral degrees in physics from MIT, and for over 30 years has worked at the Lawrence Livermore National Laboratory as a physicist in the field of high current particle accelerators and intense beams. Mr. Schiffler received a Bachelor of Science degree in physics and applied mathematics from Western Michigan University and a Master of Arts degree in astronomy and astrophysics from the University of California at Berkeley. During his graduate studies, he fell in love with teaching and entered the educational profession. He's a well-respected science teacher at Granada High School. So please welcome George and Tom.
Thanks, Chuck.
Take care. Thanks so much. Take care.
Good morning. Thanks for coming to the presentation. This morning we want to tell you about kind of a new twist on an old approach to treating cancer that we hope will become much more widely available than it is today. And cancer is a disease that touches just about every family. Mine is no exception. So I'd like to dedicate this presentation to the memory of my cousin's wife, Antoinette Ruggiero, that passed away on New Year's Day after a 2-year battle with cancer. And to kind of introduce the subject and put it all into perspective, I'd like to show a short film clip that was prepared by CNN when they visited the laboratory.
Proton therapy is considered the most advanced form of radiation therapy available, but the setup is massive and so is the cost. That could be changing, though. CNN's Jackie Jarris takes a look at this week's next big thing.
The use of radiation therapy is a critical tool in the fight against cancer, but proton therapy, a newer, more precise type of radiation therapy, is limited because the machines are the size of basketball courts and cost near $150 million each. Only about a dozen of them exist throughout the world. Unlike the more common X-ray radiation treatment, proton therapy allows doctors to treat cancer with a maximum dose of radiation while minimizing effects on surrounding tissues.
Now, the great thing about the protons is that they go into the tumor and they drop all of their energy in the tumor, so they're not coming out the other side.
Just like the magnets that thrust this roller coaster into high speed, magnetic fields accelerate protons into a patient's body. Now, researchers are close to shrinking the technology to the size of an MRI machine.
We could actually fit a proton therapy machine into a very small compartment that would allow proton therapy to basically be spread throughout the medical system in the United States.
The medical technology company Tomotherapy expects to bring the new system to market within 4 years, and while not a cure, researchers hope it will be a powerful and accessible weapon in their fight against cancer.
We'd like to eradicate cancer. We'd like to treat it safer and more effectively. And this machine is one great step along that way.
Jackie Jarris, CNN.
So here's an outline of what we're going to cover this morning. First, we're going to start with some definitions so we have a kind of a common language to talk about some of the problems and solutions. I'll spend a little bit of time discussing how radiation can both cause cancer and can be used to treat cancer. And in particular, why we're interested in using protons to treat cancer, what conventional proton therapy systems look like, and there are a number of them out there, and talk about a type of accelerator called a dielectric wall accelerator that we've been developing at the laboratory, aimed for a completely different purpose, and how that can be applied to proton therapy. So the first definition let's start out with is voltage. And on the left side of the screen, you see a little diagram of an electrical circuit. That thing labeled V sub B represents a battery, and the arrow labeled I represents a current flow in the circuit. So the best way to think about voltage, if you're not familiar with it, is to think of water flowing through a garden hose. And the pressure difference is what drives the flow of water through the hose. And pressure is similar to voltage in that respect. So voltage drives electrical current through a circuit, and the current is basically the rate of flow of electrical charge through a circuit, and very similar to water flow. Now the green object labeled R is an electrical symbol for a resistor, and that represents something that impedes the flow of current. So you can, the analog for a garden hose is putting a kink in the hose. That restricts the flow of water, and you can overcome that if you increase the pressure. And voltage differences actually drive the current. There are some examples here of different devices and different voltages attached to them. Everybody's familiar with a 9-volt battery, and your normal house service, 110 volts. You'll be seeing a demonstration later on where there's a 350,000 volt apparatus. And of course, the most impressive would be lightning, in which the voltage difference between a cloud and the ground can be several hundred million volts. So remember that will come in handy later on in the talk. And associated with voltage is a quantity called electric field. It has dimensions of a voltage difference divided by a distance. The unit is a volt per meter. And what you see on the left-hand side of the screen is a circuit diagram for an object called a capacitor, which is hooked to a battery. So imagine you have two parallel conducting plates, one colored red and one colored blue. And to start out with, they're electrically neutral, they're uncharged. And you hook up a battery to it. And what the battery does is it yanks some electrons out of the red plate and pushes them onto the blue plate. So the whole object itself is still electrically neutral, but you've unbalanced the charge distribution, moved it from one plate to the other, and you speak of the capacitor as being charged. As a result, there's an electric field. You see the little arrows that point from the plus signs to the minus signs. And associated with the electric field is energy. There's energy stored in that field, and the capacitor is an energy storage device. Also, if you imagine you have a charged particle, and the little red thing there with the plus sign, if that's in an electric field, there's actually a force exerted on the particle, which is given by the bottom equation. It's the product of the charge on the particle multiplied by the electric field. That gives you the force. And by Newton's law of motion, that also gives you an acceleration. So that's the thing to remember, is if you have a charged particle in an electric field, it can accelerate that particle along the direction of the electric field. Now, if I took that red particle and brought it over to the red conductor and let it go, the electric field would increase its speed, accelerate it, and slam it into the blue conductor. And that particle would gain energy. And the amount of energy it gains would be equal to the product of the charge that carries multiplied by the voltage difference through which it moves. And the unit for that is the electron volt. It's a very small amount of energy. A more convenient unit that we'll use is the MeV, which stands for a million electron volts. Next definition we need is that of an atom and a molecule. These are the basic building blocks of all matter, including biological tissue. And the atom, shown on the left, consists of an inner core or nucleus. The nucleus contains heavy charged particles called protons, positively charged, and neutral particles called neutrons. And at a comparatively far distance outside of the nucleus, you have smaller particles which are negatively charged. They're electrons. They have the same charge as the proton, but an opposite sign. So a normal atom is electrically neutral. You have as many electrons as you have protons. And atoms can form associations with other atoms of the same type or other types. They can form molecules, shown on the right. By sharing electrons, they can form chemical bonds. And so this is a famous molecule, a water molecule. It's oxygen and two hydrogens, and you can see the electrons here. And as Tom points out, if you flip it over, you have, there you go, Mickey Mouse, right. That'll appear in a quiz later for credit. Next definition we need is that of ionizing radiation. Now, there's lots of types of radiation. There's radiation in your microwave oven and infrared radiation. But what we're talking about here is ionizing radiation. And what we mean by that is that's any particle, charged or not, and an electromagnetic wave that has sufficient energy that it can knock an electron out of an atom or molecule. And there's some examples shown on the right-hand side. Alpha particles and beta particles are charged particles. Gamma ray is a very energetic electromagnetic wave. X-ray is similar, it's a little less energetic. And a way to detect this is with a familiar Geiger counter. So the animation at the bottom of the slide shows a Geiger tube which has a central wire and a cylindrical outer conductor, and there's a voltage applied between those two. And it's filled with a gas that doesn't permit current to flow. But ionizing radiation that gets into the tube is able to dislodge electrons. And those electrons can be collected on the wire, and when amplified, you can actually hear them. You can hear a click of a Geiger counter. And Tom has an example he'd like to show you.
So we've got a radioactive source here. This radioactive source was $1.79 at the grocery store. There's a salt substitute. Normal table salt is sodium chloride. This is potassium chloride. Potassium, it turns out, is a naturally radioactive element. It is a fairly weakly, it's actually a very weakly radioactive element though, so for those of you who had bananas with your breakfast, don't expect your mutant powers to kick in anytime soon. If I pour out a little bit here and turn on the Geiger counter, every click you hear, let me get the microphone a little closer, every click you hear is ionizing radiation from the potassium hitting the Geiger tube, taking this gas in the Geiger tube that when it's neutral is an insulator, but the ionizing radiation knocks the electrons off this gas, the gas becomes a conductor, completes the circuit, it's amplified, and you hear it as a click. So, bon appetit.
Thanks, Tom. Okay, so ionizing radiation, if it gets inside a cell, can do biological damage by this mechanism. If you take an atom and hit it with ionizing radiation and kick out its electron, it'll be very unhappy. It wants that electron back, and it'll try to get it from wherever it can. So if it comes in contact with a neighbor atom or molecule, it'll try to yank an electron out of that, and that can disrupt that molecule. And that process can continue. Those poor unfortunate fragments will go off and find their nearest neighbors and try to disrupt them. So in every cell, we have DNA, which is the master blueprint for basically how the cell can reproduce an exact copy of itself, and that can be damaged by the ionizing radiation. Now, there are cellular repair mechanisms that repair the damage, but if there's enough radiation, you can overcome that and create some copy of the cell that you don't like, and those things can increase and multiply and develop a tumor. Now, I don't want to leave you with the impression that most cancer is generated by radiation. It isn't. It turns out that in every cell in the body, DNA is being damaged at least 1,000 times a day in every cell, just by normal metabolism. So just by the function of being alive, your DNA is under constant assault, and it's also under constant repair. But that mechanism can occasionally be overwhelmed. So if you imagine that you can do that damage and cause cancer with radiation, you can also apply lots of radiation and do lots of damage to a cancer cell and kill it. So here are some sobering statistics. During their lifetime, 1 in 3 people will develop cancer. That's a pretty nasty number. Of those people, about half of them will be treated with radiation, and for most people, that means X-ray radiation. So there are more than 2,000 locations in the United States where you can get this kind of therapy. And the machines, there's one shown on the left there. They're relatively small. They cost a few $1,000,000, which sounds like a lot of money, but it's actually cheap when compared to the cost of proton therapy, as you'll see. These machines fit in a single room. The room is shielded, to be sure, to protect people, people in the hospital from the radiation, but you go 15 miles in any direction in a populated area and you go run into a clinic that can do this. So I'm going to show you a short little animation that compares treating a brain tumor with protons and X-rays. You'll be able to compare the two. So there'll be a tumor centered, the center of the brain above the optic nerves. And first, an illustration of proton therapy treating that tumor. Notice the protons come in and they don't go out the other side of the tumor. Now the same thing with X-ray therapy. Notice the X-rays come in and they go through the tumor and out the other side. Here's a side-by-side comparison. Okay, so if you look at these and look first at the X-ray therapy picture in the lower portion of the screen and proton therapy in the upper portion, you notice immediately that X-rays are coming out the other side of the tumor and protons are not coming out the other side of the tumor. So we refer to that as an exit dose. So protons have no exit dose. Now, if you look at the color in the X-ray picture at the bottom, I could find my pointer here, you notice that this area has a darker shading than this area. That indicates that there's more dose being deposited here than there is here. There's also more dose being deposited here than in the tumor. This is the entrance dose, and it's very high with X-rays. It's comparatively smaller with protons. Now, if you ask, what sets the limit of dose deposition for treatment to a cancer patient? It's not the dose you put in the tumor, it's the dose you put in the healthy tissue. It's the dose you put in the entrance and the exit into healthy tissue that limits how many X-rays you can pump in. And so because protons have less exit dose and no exit dose and less entrance dose, you can think about being able to deliver a higher dose to the tumor without causing correspondingly more damage to the healthy cells. Another very important point, with X-ray therapy, if you have a cancer that you treat with X-rays and it comes back in the same spot, generally you can't retreat it with X-ray therapy because you've done so much damage to the surrounding healthy tissue, it's just not an option anymore. But in many cases, you can treat that area with protons. And because there's no exit dose, you can think about treating tumors that are very close to critical organs and structures like the spinal column. So this shows it in a little bit more detail, why there's a difference between these two methods of treatment. So if you look at this blue curve, this is how the dose is deposited in water, which is a good model of the human body. Human body is mostly water. So 0 on the scale here would indicate the surface of the body. This is the skin. And this is depth into the body. And the vertical scale is the relative dose that's deposited. You notice with X-rays, you deposit most of the dose very close to the surface. And the dose just sort of gradually falls off and it goes quite a ways in. If you look at any of the other curves, those represent the doses, the dose distribution that's left by protons of different energies. So look at the green curve, for example. You see that there is an entrance dose, but it's a lot smaller than what you get from X-rays. And as you go into the body, that dose increases until it reaches a maximum and then very quickly falls to 0. And then there's nothing beyond that point. And by adjusting the energy of the proton, the energy that the proton comes into the body with, you can move that peak around to different distances. So if you look at the range of tumors you'd like to treat in the body, it turns out you need between 70 and 250 MeV worth of protons. 70 MeV is just used to treat tumors in the eye. It's a very shallow depth. To treat a deep-seated tumor in a large person, you need 250 MeV. Now compare that to the energy that you need to produce the X-rays for normal X-ray therapy. And a 6 MeV electron beam is sufficient to produce that X-ray profile. So you make X-rays by accelerating electrons and slamming them into a thin metal target, and you get X-rays out. A 6 MeV machine is a whole lot smaller than a 250 MeV machine. That's why X-ray machines are sort of all over the place and they're relatively affordable. But there are proton therapy centers. And this is a diagram of a typical one. They mostly look like this, and actually the newer ones are actually larger. But there's a circular accelerator here. We'll zoom in a moment. There's a machine called a cyclotron here, a circular accelerator that's quite large. And there are 4 treatment rooms. 3 of these things have large structures called gantries that are able to take the beamline and actually rotate it around a patient lying on a couch, complete 360-degree revolution. The 4th room usually has a beamline that comes in at a fixed direction. And this is done to try to make these centers somewhat economical. The rest of the space is taken up with various diagnostic and patient meeting rooms. Whoops. Zoom in here. So we're going to zoom in first on the cyclotron, which is the source of the protons. Let me stop the film there. And what you can see is a beamline exiting the cyclotron, and all these objects are magnetic lenses which either act to focus the beam and keep it together from blowing up radially, or act to bend it around. And you can see there's a bend going off into a treatment room. These things are like switch tracks on railroad tracks. And at any one time, beam is only being delivered to a single treatment room. In the other rooms, patients are being set up and aligned. It turns out that to do an actual treatment takes maybe 1 to 2 minutes, but it takes a lot longer than that to align the patient properly so that the beam goes in the right place. So here's a photograph of one of these gantries, of the person standing next to it. They're as high as a 3-story building. They're made to exact engineering standards so that they don't bend any more than a millimeter. This is so that the proton beam will go in exactly the right place where you intend it to go. Right now, there are only 9 places in the US where you can get this kind of treatment. Up until a few years ago, there were only 5 or 6 centers. More are planned, but they cost over $200 million each. And in today's economy, they're not being rapidly built. So now our part of the story comes in. How did we get involved in proton therapy? The type of accelerators we normally work at the laboratory are used for quite a different purpose, and they're much more powerful. So it turns out we've been working on accelerators for the nuclear weapons program, and these things are used to monitor the health of the nuclear weapons stockpile and ensure that we still know how to design these things and that they'll work as desired. So you imagine what an atomic bomb looks like. It contains nuclear fuel that's surrounded by high explosives. When the high explosives go off, they actually implode or compress the nuclear fuel down to a small volume, and nuclear reactions occur that give you the nuclear yield. Now, we can't do testing like that anymore, and haven't for many years. So what is done is you make a model of the atomic bomb, but replace the nuclear fuel with an inert material that doesn't produce any nuclear yield. But you still surround it with the high explosives, and you detonate it. And when the explosives go off, they compress that inert material, and you want to study how that inert material actually moves and compresses. And so what you want to do is at a particularly interesting point in the compression, you need to take an X-ray of it. The X-ray needs to be very fast because the object's very rapidly moving. And if you don't take the picture very quickly, you'll get blur on the image. So we built these very powerful accelerators. There are 2 of them here shown at Los Alamos. These objects that you see up at the top here, these are trucks in the parking lot. So there's an accelerator in each building. They both point to at this point of intersection, that's where your experimental object is placed. These things are enormously powerful, very expensive. Over 20 years ago, when these buildings were built, they cost over $20 million. That's without the accelerators. The picture on the left shows an example of a French version of the radiography machine. It's over 50 meters long, very expensive. And so we've had an interest in trying to make these things a lot smaller and hence cheaper so that we could have more of them and do more experiments of this type. So we've developed an type of accelerator called a dielectric wall accelerator. And the intended purpose was to take that type of technology and be able to shrink the length of one of these machines by about a factor of 10. And a colleague who used to work at the laboratory but now works at the UC Davis Cancer Center was aware of this work and asked if we could make a very small proton accelerator. And when he asked the question, none of us had heard of proton therapy, and he was instrumental in getting the laboratory and UC Davis Cancer Center to fund an initial feasibility study. We looked at it for a couple of years and decided this thing's going to be really hard, but it looks like it's possible to do it. So to explain how it works, we now have to delve into how accelerators work. So extra credit if you recognize what that is. All right. So the important point is that accelerators work, in contrast to what CNN said, not by magnetic fields, but by electric fields. Electric fields accelerate charged particles. And so we're going to look at 2 different ways to do that. One way that's pretty easy conceptually is shown at the top. So imagine I wanted to make a 100 MeV proton accelerator. That's kind of in the range you need for cancer treatment. So go down to Radio Shack and buy yourself a 100 million volt battery. It's one thing you could do. And hook it up across this tube. And let's make the tube about 6 feet long since we'd like the accelerator to be small. And we see a proton there, that little red circle with the yellow cross. And the red arrows represent electric fields. So if we put a 100 million volt battery, attach it from one end of this tube to the other, we'll get electric fields that extend throughout the whole structure. And if I introduce a proton at one end and let it go, it'll be accelerated and it'll come out the other end with 100 MeV worth of energy. Now, remember when we talked about lightning and how a typical voltage between the cloud and the ground was 100 million volts. So imagine applying 100 million volts across a tube that's only 6 feet long and expect lightning not to move from one end to the other. It'd be pretty unlikely. But there's another way to get the same result. Since what moves the particle is the electric field, you don't need to supply the electric field over the whole structure if you're just going to have one little proton going through there. You just need to supply the proton with an electric field just where it is. And so you can imagine some scheme of doing that in which you locally supply the same electric field to the proton. You could use a much smaller battery in this case now. And you just move that source of electric field with the proton as it's going from one end to the other. And when you're done, the particle will come out with 100 MeV. But you don't have this massive voltage applied across the tube. So it looks like the electric field that accelerates the particles has been pushed by a wave. And to get a little bit of insight into that, Tom's arranged a demonstration.
Well, I want to thank the Granada High School students who are sitting in the front row that are going to help me with this demonstration. They're going to be these components of a particle accelerator. And the way it's going to work is I'm going to play the part of a proton injector. I'm going to inject the proton into the accelerator. Students are then basically going to do the wave just like you would do at a ball game, except surfing along this wave will be the proton.
Very good. Thank you. I think you guys almost needed a couple of focusing elements to keep the beam in line there. So how do you actually implement this in an accelerator without actually attaching students into it? So what I've got here is a frame from a simulation that actually shows how this thing would work. And notice I have a little red rectangle there, which indicates a device that we'll describe in the next slide called a Blumlein, which actually acts like a student in that it's a local source of electric field which just turns on at the right time. And we've built an accelerator structure by stacking a whole lot of these things together, and they're going to be triggered at different times. So each one produces an electric field just locally, just for a little bit of time, but they all turn on at different times. The idea is to generate a traveling wave of electric field. That's the red area. I'll stop the simulation here. This graph is showing this single hump of electric field that's propagating down the axis. And the idea is you want to bury your proton right in the middle of this red area, which indicates the electric field. So how do we actually, what is that red rectangle? It's important to understand that. That's the heart of the accelerator. So what we're going to do is take that rectangle, lie it down on its side. We're going to rotate it counterclockwise by 90 degrees and kind of look at how it works. So this device is called a Blumlein pulse generator. It's named after Alan Dower Blumlein, who probably nobody in the audience except Art has heard of before. This guy was a genius, a British electrical engineer. At age 7, he repaired the doorbell to his house and handed his father a bill saying, repair so-and-so, Alan Dower Blumlein, electrical engineer. This man invented stereo, invented surround sound, and died in 1942 in a military plane crash where he was developing radar for the Allies during World War II. He also had a hand in early development of television. But what the structure looks like, it looks like two capacitors. Instead of being arrayed vertically, they're horizontally. And you see that, so each one is attached to its own battery, and you see the red arrows indicate the direction of the electric field. So these capacitors are charged. Remember, charged capacitor stores energy in the electric field. Notice the electric fields point in opposite directions. And the right end of this thing is the end of the Blumlein that actually touches the beam tube. So in this picture, the beam tube runs vertically. And initially at this point, because the arrows point in opposite directions, there's no net electric field. So if I were to throw in a proton past the edge of that structure right now, it would get no net acceleration. So I'm going to remove the charging supplies here. The capacitors are still charged. And now you'll notice in the lower capacitor I have this switch indicated by that arrow. And the switch connects the top electrode of the bottom capacitor to the bottom electrode. And now I'm going to close the switch. What that means, closing the switch, is I've now connected the top and bottom electrodes of that bottom capacitor. Now that should mean that there's no electric field there because I've directly connected things which are at different voltages, and they can't be at different voltages when I connect them with a good solid wire. So the voltage there has to go to 0. Well, you would think that your intuition might tell you that the voltage in the entire lower half collapses instantly, but it doesn't. The reason it doesn't is electrical signals don't travel instantaneously. They travel with a speed close to the speed of light. So the information that there's now 0 voltage at the left end of that line can only propagate at a finite speed. And so I'm indicating that wave propagating to the right that's carrying the information that, hey, behind me, there's no voltage. Up ahead, those guys haven't gotten the word yet. They don't know. Now, when this wave hits the right boundary, that's the time I want the protons to be there. So I've arranged when I close the switch so that the proton beam shows up at that instant. It turns out that that right-going wave bounces off the right end of that line. A portion of it gets reflected and starts going back toward the left. Another portion of it actually wraps around into the upper line, and you'll see a wave start to propagate to the left in both lines. Now notice that those arrows are both pointing in the same direction. So at this point, there is now a net electric field and a voltage difference between the top and bottom of that whole structure, and you see the plot coming up there. Waves are propagating in both lines off toward the left. When they hit the left boundary, they bounce off again, and you get a reflection toward the right. And you see the arrows are disappearing, and now the voltage has collapsed. All the energy is gone from inside the capacitors. It's completely removed. It's all gone, ideally, into the beam. And then it's off. And this is what some of these things look like in the laboratory. So there's a stack of 7 of these lines, put one on top of one another, and they're only about that long. And they generate pulses that last for 3 nanoseconds. So a good way to think about a nanosecond is to think about light speed. Light speed is very fast. So light is fast enough that it can encircle the Earth more than 7 times in 1 second. That's really fast. A nanosecond is the time it takes light to move 1 foot. So it's a really small unit of time. And these devices about that long produce a 3 nanosecond long pulse. Now, okay, so now we know what the structure of the accelerator is. What determines how short you can make the accelerator? You know, can we make it arbitrarily short? Something must limit that. What limits it is electrical breakdown. What do I mean by that? Well, breakdown is the failure of electrical insulation. What's electrical insulation? It's something that doesn't allow current to flow. So there are common examples like glass, that's an insulator, oil, antifreeze, dry wood, paper, rubber, most plastics. Every insulator will fail with a large enough electric field. So it's that's going to limit the size of the accelerator. So we need to get a little bit of insight into that. So now, Tom with a hair-raising demonstration here.
So this is a device called a Van de Graaff generator. It generates a static electric charge. The principle is the exact same if you've ever walked across shag carpeting and stocking feet and received a shock. Well, this is the same thing, but a little bit more powerful than that. There is a rubber belt inside this thing that rubs against some metal mesh that builds up a static charge of electricity on the metal dome. If I touch that to another conducting surface, those charges will spread out, in this case, onto these little metal foils. And since all these foils are becoming like charged and like charges repel, these little foils are repelling each other, just like the girl in the picture. Turn this off for a second, move this out of the way. So now, right now, if I turn this back on, between this metal sphere, which becomes charged, and this one, which is neutral, there's air. Air normally acts as a good insulator. But when I turn this back on, this becomes negatively charged. Even though the charge on this sphere remains neutral, the positive charges come over here. They're interested in the negative charges over here. The negative charges are repelled, and that sets up an electric field. When that electric field becomes powerful enough, there will be a breakdown of the insulation made up of the air, and you'll see a spark. This is exactly what we don't want to have happen in the particle accelerators.
Thanks, Tom. So as Tom just showed you an example of breakdown in the air, of course a really spectacular one is lightning, shown on the upper right here, but you can have breakdown in liquids. The nice thing about electrical insulation that's a gas or a liquid is it recovers. You notice you got repeated sparking there. You depleted the voltage, the air became a good insulator again, and then was repeatedly broken down. If you break down a solid, it's toast. You can't use it anymore for that purpose. And sort of a general characteristic of most types of insulators is that if you apply the voltage for a shorter and shorter time, you can usually get away with a higher and higher voltage before you get a breakdown. That's a sort of a very key strategy that we'll be discussing for how we make the accelerator small. Breakdown can also occur along the boundary between different materials. Maybe a little difficult to see this. It looks fairly dark here, but on the left, what we have is a picture of the interior of a vacuum chamber to which most of the air has been pumped out. Have an electrode in the top and bottom across which a pulse voltage is applied, and a dark material in between those electrodes is a section of beam tube material that's an insulator. And on the right is a picture of that breaking down right along the boundary between vacuum and the insulator. So this is a particularly weak point in the accelerator. So if you imagine you're going back to our example of a 100 million volt battery across this 6-foot long tube, where you would expect to have a breakdown is right along the inside diameter of that tube, right along the inner surface, where you have a boundary between the insulator and vacuum. That's an electrical weak point. So we use 3 different techniques to try to combat this. One is we use a novel beam tube called a high gradient insulator. And we have plenty of experimental evidence that this thing works, although we don't know exactly why. So if anybody really wants extra credit, come and explain to me how this works, and I'll be very grateful. But what you actually do is you take your favorite insulator, plastic, glass, whatever, Take a solid piece of it and slice it into very thin layers. And then glue it back together. But between each of those pieces, you now put a very thin conducting sheet. And you don't electrically hook the conductors to anything. You just sort of glue them to the thin sheets of insulator. Put that back together. You can see on the extreme right-hand image is a magnified view of the surface. And you can see these sub-millimeter laminations that show the detail of the structure. The other strategy is you use very short electrical pulses. You know, it's not nice to fool Mother Nature, but if you do it really fast, sometimes you could get away with it. And so that curve shows the general trend. As you go to shorter and shorter pulses, you can stand higher and higher field stresses before you have a breakdown. And for high gradient insulators of this type, it looks like if you apply pulses around a nanosecond, you can withstand something like around 100 megavolts per meter. That might allow you to have a 200 MeV accelerator that fits in 2 meters, a 2 meter length. And the third thing you do is you use advanced materials that have intrinsically high breakdown strengths as some of the components. And in particular, you use this for a switch. Remember, we talked about a switch as a necessary ingredient in the Blumlein. You have to close the switch at the right time so that you generate the pulse just at the right moment that the proton is going by, so it'll get accelerated. And the way you make a switch is you take this material, silicon carbide, which is shown in the top illustration. The silicon carbide is an artificially grown crystal. It's a very rugged material. And if you can grow it without defects, little bubbles and divots in it, it has a very high breakdown strength, hundreds of megavolts per meter. The way you turn it into a switch is you put contacts, electrical contacts on the top and the bottom. Now, normally, the silicon carbide acts as an insulator. It does not allow current to flow. But if you inject laser light in through the side of the wafer, look at the little yellow arrow there, a pulse of laser light coming in from the side will actually liberate electrons inside the silicon carbide. You can do this very quickly so that you can very rapidly turn the insulator into a conductor. And that acts just like you've closed the switch, just like you've thrown a lever. And when you remove the laser light, it turns back into an insulator. And here's a picture of it, of one of these switches shown deposited in a Blumlein. They're very small. We make them about the size of a postage stamp, a centimeter on a side by about a millimeter thick. Triggered by light, and here's how you make the accelerator, how you put the whole thing together. You start out with a beam tube of this high gradient insulator configuration, stacks of Blumleins. Here are the photoconductive switches, and the way you get the timing right is you have a laser, one laser that triggers everything, and you feed the laser pulses to the switches through a network of fiber optic cables. Now, light, again, does not travel through these cables instantaneously. It takes some time to propagate through. And by arranging for those fiber optic cables to be different lengths, you can arrange the arrival time of the laser pulses to the different switches to be different. So the laser light can arrive in sequence and give you the right timing for the accelerator. And Tom has an example of one of these things.
So this little pretzel-shaped thing here is just made out of a clear plastic. What happens when I shine laser light into it, this is just an ordinary green laser pointer, is that laser light internally reflects on the inner surface of this pipe. The laser beam just kind of bounces around until it gets to the other end. So that way you can send a signal, and that signal is sent through this optical fiber, and the signal is sent with light. That's exactly what's going on to trigger the Blumleins.
Thanks. The nice thing about that fiber optic distribution system is you can kind of twist it into a pretzel and the light still goes through and comes out the other side. Makes it very handy when you're bending things. So we've been working with two companies to develop this for use in proton therapy. The first company we worked with was Tomotherapy, that actually makes X-ray therapy units for cancer. They licensed the accelerator technology from the laboratory and provided initial funding for development. And then they spun off a new corporation called CPAC, the Compact Particle Acceleration Corporation, which has a facility very close to the laboratory, just on the north border. And the laboratory has a research and development agreement with them, and they've taken the lead in developing this for proton therapy. They hope to have their first product to market in about 2 to 3 years. So in summary, I hope we've convinced you that proton therapy is a potentially superior form of radiation therapy, that this dielectric wall accelerator, if successfully produced, promises to dramatically reduce the size and cost of these machines and making them more widely available. And the ultimate objective is to be able to get it small enough so we can fit it on a small gantry and put them in your local clinic. So, come to a clinic near you. I'd like to thank a number of people that helped put this together. Tom and I would like to thank Dick Farnsworth and Marcia McGinnis, who made these slides look really nice. The Lawrence Livermore Laboratory and UC Davis Cancer Center that provided the initial funding to test out the feasibility of this idea, and who continue to provide encouragement and support for its development. In particular to the Beam Research Program at the lab that did the early development work, and to Tomotherapy, and of course to CPAC that's now has the flag and is developing this. So I'd like to thank you very much for attending again. Appreciate you coming out on Saturday.